Please.
Hello? Okay, cool. Alright, last one, almost there. So first I want to thank the organizers for bringing us all here and giving me a chance to talk about some progress on my thesis, which has to do with noncommutative geometry, which is the study of noncommutative operator algebras. So it's kind of a misleading name. It's actually a study of algebra, but you're using geometric intuition. So that's the origin of the name. And my thesis is about how you can get a different approach to it, try to understand it a bit better using some ideas from quantum foundations, specifically the Contextuality theorem and contextuality, which might seem surprising, but I think it makes sense to think about it for 2 years. Okay, so first I'll go over Delphine duality, which is the basis of noncommutative geometry, and talk a little bit about the program of noncommutative geometry, which is actually a huge mathematical field, hundreds of researchers, and it's known for being quite tedious and complicated, but that's because you're studying geometric spaces that don't actually exist, and you're doing it entirely using algebra, so you're trying to describe spaces that exist using algebraic, very tedious algebraic tools, and hopefully we can try and get around that using some ideas from contextuality. Then I'll talk about my approach to noncommutative geometry, and talk about some recent results. Okay, so first of all, Delphine duality is an equivalence between a geometric category and an algebraic category. The geometric category is the category of compact Hausdorff spaces, and the algebraic category of commutative unital C-star algebras. And that's a quite clear physical interpretation, which is the algebraic category, commutative unital C-star algebras, are like algebras of observables for commutatives for classical systems, and geometric spaces are like their pure state spaces. So this is like reflecting the state observable duality in the classical case. And our goal is to try and explicitly find the geometric dual, the geometric dual for noncommutative C-star algebra. The noncommutative C-star algebras are used to describe algebras of observables in quantum theory. So we could find a geometric dual. It would be analogous to finding something like a pure state space. But it's not quite that simple, but okay, we'll get to that. So Delphine duality is, by saying that commutative unital C-star algebras are basically exactly the same as compact Hausdorff topological spaces, they form the basis, the motivating metaphor for being able to study non-commutative C-star algebras as if they were spaces. Okay. So the geometry of non-commutative C-star algebras has been studied for decades by mathematicians, but it's been done indirectly using algebraic techniques. So the idea is, if you have a topological space, X, and you take all the continuous complex value functions on it, C of X, you get a commutative unital C-star algebra. And because these categories are equivalent, you can rephrase any topological concept in terms of the algebra. Right, so if you have a non-commutative algebra, Delphine duality no longer applies, but you can still use it as a motivating metaphor. So you just sort of pretend that for a non-commutative algebra A, that there is some space X for which A is equal to the continuous complex value function of X, even though there isn't. You just pretend there's an underlying space there, which would, in quantum theory, sort of represent something analogous to pure state space. You just pretend it's there and study it as if it is there. But the thing is, you don't have access to the space because it doesn't exist. So you have to work on the algebraic side of the duality rather than the geometric side. So the way you use it is you use Delphine duality to translate all your topological concepts into algebraic concepts. Right? So you build up a dictionary and study it entirely using algebraic terminology, using only the algebraic terms. And you use the commutative case as your guide. So, for example, if you have a space X, a continuous real value function on it is the same thing as a self-adjoint element in C of X, the continuous complex value function on it. And you can keep going like this. In a closed set of a topological space, right? Then you just consider all the functions which vanish on that closed set. And you get an ideal of the algebraic functions on it. If you multiply a function which vanishes on some closed set by any other function that's also going to vanish. Right? So you can then prove a theorem saying there's a bijection between closed sets of the topology and closed ideals of the algebra functions on it. And then you just write this into a dictionary entry and pretend for non-commutative algebras that closed ideals are like closed sets of this non-existent space. And you just keep doing this, and you see that it goes beyond topology. You can do measure theory. This is a bit suggestive of relation to state space, because the Cartesian product of classical state space is how you join systems, and that corresponds to tensor product. You can go to really crazy differential geometry, but the starting point is that you have some C algebra which represents topology, and then you put extra operators here and such. Okay? So the normal way, the canonical way of going about it, which is the reason why it's so complicated, is that you use Gaussian duality to translate topological concepts into concepts about commutative C-star algebras. These are equivalent, so you just move concepts over by translating it, and then just applying those concepts without modification to non-commutative C-star algebras. As you notice here, none of these actually rely on on the algebra being commutative, so you can sort of apply them without modification to non-commutative case. Now, I'd like to find the geometric side of the duality for non-commutative C-star algebras, which doesn't exist. And the way of going, my way of going about it is to associate some geometric objects with the non-commutative C-star algebra, and then showing that it comes automatically equipped with a way of doing this translation process by doing it through the geometry. So it comes with a way of applying topological concepts directly to the geometry, and agreement of these two methods, the canonical method that's been studied for decades and this new method that goes through this geometric object, that would justify considering the geometric object to be the underlying geometry of an object algebra. Okay, so the proposal is to replace topological space as what spectrum of a C-star algebra should be with a diagram of topological spaces. And the inspiration from this comes from the Aisha-Butterfield approach to contextuality and Contextuality. But with some modifications to make it work in the way that I just mentioned. So what we do is we Functorial associate to every C-star algebra not a single topological space, but a functor whose codomain is topological spaces, so a diagram of topological spaces. Okay, so if we have an algebra A, consider the subcategory of commutative C-star algebras whose objects are the contexts of A. So context is another word for commutative subalgebra. Whose arrows are the inner automorphisms of A that have been restricted to a context. So they're like the non-commutative symmetries. In the commutative case, the inner automorphisms are just the trivial. Okay? So that's a subcategory of commutative C-star algebras that associated to A. And that has an inclusion functor into commutative C-star algebras. So if we just compose that with the spectrum functor, we now get a functor whose codomain is topological spaces. So it takes all the contexts and gives you like a state space for every context. So that's why I just call them contextual state spaces. Okay, so we take a non-commutative C-star algebra and we get a diagram of topological spaces, which is like the state space for every context, along with these arrows, which are also very important. Okay, so here's the simplest non-trivial C-star algebra, the 2x2 matrix algebra, and here's a scheme for what that space could look like. So all these 2-point spaces are like bases, and these double-sided arrows are like change of bases, and they all have a quotient to the trivial spectrum of the trivial algebra, which is just like multiples of the identity with a single point. Now this is an extremely trivial picture, but it's sort of the only one you can actually try to draw. Usually these spaces are not discrete. There are a lot more levels, and the way these quotient maps intersect with each other is critical to the structure. The simplicity of this picture is also reflected in the fact that Gleason's theorem and Conjectures don't even work in the 2x2 case. But this is just to give you an idea of, there's all these topological spaces and maps connecting them. Okay? So given this thing that we've associated to a C-star algebra, it comes with a way of extending topological concepts to algebraic concepts. So what you do is you take a functor f, which acts on topological spaces and sends you to some suitable category C. We can now automatically turn that into a functor that acts on C-star algebras and sends you to C, but which agrees in the commutative case with the topological functor. And what you do is you simply apply f to every one of those topological spaces in the diagram. So that gives you a diagram in C, and you just paste it all together. Take a limit or the colimit depending on whether the functor was covariant or contravariant. Paste it together along using these arrows to get a single object in C, and compose those steps together, and then just gives you a way of extending any topological functor to a single category to one that acts on all C-star algebras. In the commutative case, in the C-star algebra commutative, it's the exact same thing as the original topological functions that are met with. So intuitively, it's like taking this non-commutative space, which doesn't exist and can't be visualized, and sort of taking all of its quotient spaces, some of which will, some of them are non-commutative spaces, and we just forget those, because some of them end up being actual topological spaces, and those are the ones that are tractable, ones that you can work with. So you take a non-commutative space, decompose into its quotient spaces, keep the ones which are tractable, topological spaces, apply the functor that you want to extend to those, and then paste it all together. And that process gives you a method for extending topological concepts to C-star algebra. Okay? So yeah, and again, we want to compare this method with the canonical method that uses Galvan duality, and it's a lot of work to translate concepts. And agreement of these methods will justify considering this space G to actually be something like the Galvan method. Okay? So first thing I did was I tried it with a very complicated topological concept, K-theory, which is a very well-studied cohomology theory, which is based on the idea of vector bundles. And that also has a very well-studied operator theoretic generalization called operator K-theory, which is, has a pretty complicated definition in terms of finite projective modules over your algebra, and is an important classifying invariant of C-star algebra. And so the operator K-theory has kind of complicated definition, kind of obtuse. So it'd be nice to have one that's actually sort of more geometric in flavor, because it is essentially a geometric theory. So I did this process with K-theory, and while it's still open whether the extension of topological K-theory is precisely equal to operator K-theory on the nose, you still actually can reconstruct operator K-theory directly in terms of the extension of topological K-theory in a simple way. You just do this harmless transformation of the C-star algebras first, which actually doesn't change the K-theory. It's something you do anyways whenever you compute the operator K-theory. You take the tensor with compact operators. And then once you've done this harmless transformation to your C-star algebra, you take the extension of topological K-theory, only retain the finite part. So, and maybe it's even true that this holds, but basically the point is that you can express operator K-theory in terms of this extension. So to continue the program, try to build more evidence, it would be nice to extend other concepts. So the next thing I tried to do was closed set. And if you remember from the dictionary, the analog of a closed set was a closed two-sided ideal of your algebra. So this leads to a natural conjecture, which was included in last year's QPL proceedings. So if I take this functor tau, which assigns a topological space its lattice of closed sets with containment, and take the extension of that, the conjecture is that it should assign to a C-star algebra its lattice of closed two-sided ideals, because that's the dictionary definition of the analog closed sets. Okay? And there's some more, so that was my original motivation for making this conjecture, just it's in the dictionary, I want to try it, see if it works. Upon further reflection, there's some more motivation, which is that this is basically saying you take an algebra, you have this diagram of topological spaces, each of these topological spaces has a topology on it, and when you take the limit of these topologies, the conjecture is that you get the lattice of ideals, but actually the lattice of ideals is itself a topological lattice of a space that you would associate with C-star algebra. Specifically, the lattice of closed-sided ideals in algebra is the same as this very important topological lattice on the primitive ideal space of an algebra A. Okay? So the primitive ideal space is a topological space that you associate with the C-star algebra. Its points are the kernels of the irreducible representation. Its topology is basically just the lattice of ideals. And in the commutative case, it corresponds, it's precisely the same Galvan spectrum. Okay, so what they're saying is you have this, all these topologies, you take the limit, and you get another very important topology. The topology of the primitive ideal space. So what's interesting about the primitive ideal space is it's actually the C-star algebraic version, or can be considered the C-star algebraic version of the spectrum functor, which is important in algebraic geometry. So you take a commutative ring R, you take its spectrum, whose points are the prime ideals of R together with this same topology, the one that comes from ideals. And then usually you give it a structure sheet, and then you study R by studying this locally ring space. Okay, so this is probably maybe a bit speculative, but if you can prove this conjecture and recover this Zariski topology, then maybe you can actually consider this diagram to be something like an enriched version of this spectrum, of this kind of spectrum. Because, it has the same topology, so you can do the same sort of sheet theory stuff, but its points are spread out, separated. You can treat them all separately. And this could possibly be a basis for introducing sheet theory techniques into non-commutative geometry and bring non-commutative geometry more in line with algebraic geometry, complex geometry, using those kind of techniques, rather than the very obtuse algebraic ones which are unique to studying non-commutative geometry. So that's an additional motivation to try to prove this conjecture. Okay. So in trying to prove this conjecture, it's helpful to introduce the concept of a partial ideal, which is just an ideal from every context, which is consistent in a way that if I have a big context and a small context, I have an ideal chosen at each one, and if I want the ideal from a small context, I just intersect this ideal with the algebra itself. Okay? Now every ideal, the whole algebra, gives rise to a partial ideal just by intersecting it with every context. And the elements of this lattice, which is like the limit lattice of all the topologies, actually correspond to partial ideals which are fixed by every unitary rotation. Right? Remember, we have these inner automorphisms that correspond to this condition. Okay, so we can rephrase this conjecture about extending the notion of ideals to say it this way: a partial ideal arises from a total ideal if and only if it's fixed by every unitary rotation. Okay? So the strategy for trying to prove this is trying to prove it. First, consider the enveloping Neumann algebra of an algebra, where it's easy to work with the ideals are generated by projections. And there's also a close link between the context and ideals of the enveloping Neumann algebra and Neumann algebra. So you can hope to conclude the general case of the Neumann algebra case. And yeah, so we prove the Neumann algebra case together with Rui. The proof is in the proceedings. And yeah, that's the progress. And yeah, thanks.
You start from a functor going into complete lattices. Isn't it more natural to take a set of complete lattices frontal? So in the topological space you get the local, and then you hope that in the non-commutative case you really get the proper frontal as a co-element of this construction. You see what I'm trying to say?
Yeah, that could be. Do you know if the ideals of an algebra give you point out?
I think the ideals of six-star algebra from now.
Okay. Oh yeah, right.
That is probably one of the main motivations.
Right. Yeah, I mean, it probably makes more sense to include that structure if you were actually going to work with it. But for the purposes of proving the conjecture, I don't think you need that much structure. Yeah, but yeah, you're right. If you were actually trying to go through with the whole program of introducing sheets and non-commutative geometry, then it might make more sense to consider this structure.
Sheets have the one of the locale, so that makes a lot of sense.
Is there a relation between your work and the work of Christian and Manuel Rice on active lattices?
I guess there's a connection in the sense that, yeah, because their active lattices has to do with using these unitaries together with projection lattice to sort of characterize the algebra. And I guess, yeah, I'm talking about projections because ideals are generated by projections, and showing that, yeah, if you have this partial structure, but also you can extend it to a total structure using this symmetry of the rotations, the unitary rotations. So it's related, but similar ideas, but there's no direct connection as far as I can see.
Okay, let's start Nadish again. Thank you. This is the end of the day. Thanks a lot. So we start again 9:30 tomorrow with coffee and breakfast.